Okay, thank you everyone for waiting. And I'd like to thank Sitabra for inviting me to this workshop. And of course, I'm here because I was one of the authors that contributed to the special issue in EPJ, special topics as well. And today I'll talk about that article, basically what how you want to, what must the economics do in order to become a full-fledged physical science, especially now in the era of big data. And then I'll continue talking a little bit about my work doing bottom-up agent-based simulations of economies, actually historical economies. So let me start by saying that besides artificial intelligence, we are also in the brand new era of big data. So this is big data. What is big data? Big data is characterized by volume. You need to have a lot of it. It's characterized by veracity. You need to be able to trust it. It's characterized by variety. You need to be very different kinds of data together. There needs to be velocity, so the data needs to arrive very quickly. Value, this is, this kind of graph is created by businesses, so of course they're interested in economic value. So these are the 5 V's, or initially they were like 3 V's, doesn't matter. What is more important is that in 2013, it was estimated that the world generated 4.4 zettabytes of data. So 1 zettabyte is what, 1 trillion gigabytes. And it is effectively what is described is that we have generated in 1 year more data than we have accumulated throughout human history. And then in the year 2020, which is not too far from now, it is estimated that this will become 44 zettabyte. And the number is expected to grow when the Internet of Things finally come online. So if for those of you who are not aware, the Internet of Things is basically, we're trying to wire up every device that we can have on our hands, not just our phones. Basically, next time my phone will talk to my shoes will talk to my spec will talk to my refrigerator. So everything will be wired up. Anything that we can wire up, it will wire up, and those will generate immense volumes of data. So we live in that kind of world. We will live in that kind of world very soon. And so we have to start rethinking how we do science in that kind of world. So we, of course, we take inspiration from existing data sciences. So if you go around and search for data science, this is a word cloud that you would find. You'll find words like predictive analytics, data mining, KDD. This is actually a conference. And then you have math, patterns, visualization, all the stuff. Okay? But of course, coming from physics, we actually know that one of the earliest data science is in physics. Actually, it's in astronomy. So astronomy is one of the first data science in the sense that they are the one who started first doing sky surveys. Effectively, they just take high-resolution photographs of the sky, the night sky, over many nights, and then they generated terabytes of data. In those days, terabytes were very large. Nowadays, of course, terabytes nothing. I go to a computer shop and I can buy 2 terabytes portable hard drive. Then that will be enough to probably store their sky survey for a week. But of course, nowadays they're doing even higher resolution, so my hard drive will not be enough. So that's the first data science. Second data science, I would argue, is high-energy physics. Again, when they actually align the beam to crash into each other, it will generate lots and lots of collisions and lots of particle reactions, and all these will be recorded in the detectors, and then they would store this, and then armies of graduate students will try to analyze the data to see whether they have discovered the particles that is beyond the Higgs boson. Okay, of course, then they will expect to win the Nobel Prize, but we can't be sure there's anything beyond the Higgs boson right now. And then this is biology. So when the Human Genome Project came in, the reason why the biologists wanted to actually map out the entire human genome was because at that point in time, computers became powerful enough to actually start built up from the entire human genome, and of course they had actual PCR technology that allows them to do it. Now you can actually do the human genome on the tabletop machine. Okay, and it's also very quickly. It doesn't take years. It takes maybe, say, 2 days, and then you have the human genome. And in Singapore, where I come from, they're already planning something called the 100K experiment. They're going to sequence the genomes of 100,000 human beings, Asians, so that they can start to their march towards personalized medicine. And of course, in a workshop like this, I would also argue that econophysics is one of the earlier data sciences, in the sense that we take the data from the stock market after it was computerized, and then we start looking for patterns inside. Okay? Now, how would a science, a discipline like economics become a data science? So first of all, if you look at economics, it is highly theory-driven. And if it's theory-driven, of course, you're out to prove theorems. And then what you want is, of course, this by an economist, that they seek mechanistic understanding. Which means that if a computer scientist built an artificial neural network that can predict the stock market down to the closest cent, the economists will discount it. They say that this is a black box. We don't know what is going on. We want to know what is going on. And if you compare that against econophysics so far, okay, so there have been 2 different areas of econophysics. So there are the people who look at data, and so that part is data-driven, and they discovered stylized facts, a lot of them. And at this point, if you just look at data, it's phenomenology. But there's also the other side of econophysics where we build models. So what kind of models should we build? And in order to answer that question, we need to first examine the scientific approach. What is it that we're doing? We're trying to do science, and how is it that scientists do science? So first of all, we have some pieces of initial data. And then after that, we ask ourselves a question. So we create predictions, actually, and then it will it needs to be tested by an actual experiment. So this, if you read Karl Popper, this is the scientific approach that he describes. And then, of course, this initial experiment will lead to more data being collected. The more data would then will allow us to refine the hypothesis to something like that is better. And then, of course, this would again call for more experimentation and leads to even more data. And of course, we keep doing. Areas. And of course, the initial data doesn't have to be a big data at all. It can be just a very small piece of data. It doesn't work so well, actually, for life sciences, even though we can do experiments in the life sciences. And the reason is because in biology, all systems are complex. So complex systems are highly history dependent. So they depend on what the organism has actually gone through. So if you do experiments, this for anthropology, the study of other human societies. So in events, in the case of these kind of sciences, where you are less able to do experiments, is there an alternative scientific approach? And the answer is yes, and it is actually a physical science that requires us to think of the alternative scientific approach. And let's compare these two. First of all, no experimentation, and largely observational. So we can collect data through observations, but we can do little or no experiment at all. So how are truths then found in astronomy? So let's think about first of all the story of Kepler. So I'll motivate that alternative scientific approach by the story of Kepler. So Kepler was a young man when he first wrote a book about music of the spheres. Of course, he didn't write it in English. He was an Austrian, so there was no Austria at the time as well, so he was in Vienna. So he wrote about music of the spheres. He believed that the known planets, the orbits of the known planets are actually circles that are circumcising circumscribing 5 Platonic solids, arranged in a very specific order. So this is Johannes Kepler. And the 5 Platonic solids, of course, the tetrahedron, the cube, the octahedron, icosahedron, and dodecahedrons. And this is what he imagined the planetary orbits would be like. So these are the 5 Platonic solids, and then these are the spheres, and the planetary orbits will be there, and the sun will be in the middle. So obviously, you can see that the Copernicus heliocentric idea has already taken root by that time. Now, obviously, Kepler has already published the book, so he is not short of followers. People are reading his books and debating his ideas, but he himself was not satisfied. He wanted to see whether he could, based on data. In those days, if your theory is beautiful, you will be acceptable. But of course, he is a little bit more forward-looking than others, so he wanted to look for data. And who has the best data at that point in time in Europe? It is Tycho Brahe. Okay, he built an observatory called Uraniborg on the island of, I don't know how, of Copenhagen, Denmark. This was funded by the Danish king. And so this particular sextant now here has a radius of 2 meters. So it's extremely large, and he did all the observations using naked eye. So he's one of the last astronomers who did naked eye observations. From after that, people started to use telescopes. But he collected very precise data just using the eye alone. And so his data was good. And so Kepler invited him to visit, to bring his data along. And then after that, shortly, Tycho Brahe died, and Kepler inherited all the data. And by mining through the data, so Kepler's original intention was to actually fit the data to his music of the spheres model. And in that model, all planetary orbits are circular. But he found that after trying a lot of times, circular orbits won't do it. So he had to look for the next thing, maybe something that is not as beautiful as a circle, but still largely circular. And he came up with the idea of trying elliptical orbits. And he tried it on supposedly he tried it on the orbit of Mars. The orbit of Mars is one of the most elliptical in the solar system. He succeeded, and then he tried the rest of the planets. They also fitted the elliptical orbits very well, and therefore he formulated the first law, Kepler's first law, that the planets move in elliptical orbits with the sun at one of its foci. Okay, so that's the first law. Of course, we know that Kepler has 3 laws. But he didn't discover them all at the same time. He discovered the first law, then he started asking more questions. Oh, okay, so what else can I find, if I assume that the planets move in elliptical orbits? Then he discovered the second law, which is in the statement says that a line joining the sun and the other planets sweep through the same area over the same time. So this is actually a statement of the conservation of angular momentum. Okay, and then after that, shortly, I don't know the time between the second and third law, but he took some time. Actually, eventually he found that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. Now, this is a very mysterious law. He doesn't understand where it came from. He just knows that it is in the data. It's highly, and he trusts Kepler's data. In fact, he understands. He was a very accomplished mathematician. The kind of computation that he did would take, what I think some of our high school graduates cannot do it anymore. So they need the help of computer, and of course Kepler don't have a computer. So what I'm trying to point out here is that the laws that Kepler discovered in Tycho Brahe's big data, these are like the stylized facts in economics. You know they are there, you don't know why they are there. Okay? But of course, following Kepler and then Galileo came along this person, Newton. So Newton summarized Galileo's point of view on mechanics, and created calculus, and then observed that the second law of motion and the third law of motion must also be true. And of course, this is famously attributed to Apple falling on his head, the law of universal gravitation. By combining the laws of motion with the law of universal gravitation, Newton realized that he could explain all the things, all of Kepler's 3 laws. So these are mechanistic insights. So these are precisely the kind of insights that economists are after. So we need to somehow move from stylized facts to mechanistic insights, and for that we need models. But let's summarize the second scientific approach. First, we start with a model. Like in Kepler's case, it was the music of the spheres. And then you go and find a rich data set that might be able allow you to verify that model. And then you make predictions on the model. And you realize that, oh dear, the model is not quite right, so you have to make a new model. And then you have to create predictions, come back and ask the data set whether it is true. And sometimes, of course, the data set tells you that, no, your better model is not better after all. You need to go to a totally different model. So this is the elliptical orbits compared to the circular orbits. And then, of course, you keep doing this over and over again. And that's the scientific approach for observational sciences. But what if you have big data? So when you have big data, you actually you don't even know the stylized facts yet. So what you need to do would be to use machine learning and data mining techniques to find all these stylized facts, these patterns in the data, and then you eliminate some of those because they can be spurious correlations. For example, the number of people drowning in swimming pools in the United States is strongly correlated to the number of movies that Nicolas Cage appear in. This real correlation. It's a real correlation. You can Google it and you'll find it. And obviously, Nicolas Cage should not be held responsible for people drowning in swimming pools. And of course, economists would be sensible enough to remove these kind of models and then keep the rest that are sensible. And then you do repeated hypothesis testing on it until you get to a point where some hypothesis will drop out at this point in time. The rest will be refined. And what you can then do would be to go from the data with the stylized facts, the empirical laws, and then you can build models where you would try to test these hypotheses to get mechanistic insights. And of course, one class of such models will be agent-based models. I'm not saying that agent-based models are absolutely necessary, but they do reflect on the ability of human beings to make decisions. So, and of course, economists believe that even the dumbest human being on earth, when faced with the prospect of giving up the $1 in his hand to buy something, he or she would have to make some decision. So we need to somehow draw some correspondence between this. So I would say that this is more like the scientific approach for big data. Okay, and of course, make predictions, test this kind of stuff, and you eliminate some of the agent-based models. And I effectively outline all this in this European EPJ special topics paper. But what is agent-based modeling? So in this community, maybe I don't need to say too much. It's a name coined by John Holland, the late John Holland, who died 3 years ago. And it's synonymous with individual-based modeling, which is coined by Grimm and Railsback in 2005, and particle-based modeling by Helbing, Farkas, and Vicek in 2000. And an agent, if you talk to computer scientists, I don't know whether there are any in the audience today, it's an autonomous software object capable of setting goals. So it must be proactive. It is able to adjust its course of action in response to changes in the environment. It must be able to react. And is able to exchange information with other agents. So this is a manifestation of its interactivity. Okay? So in order to demonstrate that the big data science approach to economics can work, we have to do something. So we pick a problem. We pick the historical network of port cities. So these are the port cities. So there's London, this is Amsterdam, this is Venice, this is the Crimea Peninsula, this is I forgot the name here. This is Alexandria. This is supposed to be Muscat, and Johannesburg. This part of India, I forgot the name. This Sri Lanka, this Malacca, this is Palembang, and then Guangzhou and Quanzhou in China. Okay, and of course, in all these ports, you would find merchants, and they would want things that they don't have. They want to sell the things that they have and buy the things that they don't have, and those things that they don't have might be produced by people far away. So you need trading vessels. I don't know why the ship is here. Maybe it will appear later. So it took me quite a while to produce this animation because I had to create the ships from the silhouettes of images I found on the internet, and I ran out of time, so some of the vessels look alike, but the Chinese junk should look alike. So what you see first is the Chinese junk sailing off the coast of China to Southeast Asia to buy spices and also to trade in silk and also ceramic, and then they go home. Okay? In those days, there's no incentive for Chinese vessels to sail anywhere further than Southeast Asia because you have to wait for the winds to change. And then after that, you have to wait for the winds to change to come back, and then wait for the winds to change again to go back to China. So a round trip would take maybe 2-3 years. So they cannot afford that kind of luxury. They rather want to go home and count their money very quickly. So that's usually just a 1-year trip, here, down, and back, shorter than a year. Okay? And of course, the Southeast Asian vessels can sail to Sri Lanka or India with the new goods and also the spices. And Indian vessels can sail to Southeast Asia. That's how the Indian influence spread across Southeast Asia. And of course, the Arab ships can sail to Southeast Asia, India and Sri Lanka. They can make their way back with Chinese silk and Chinese ceramic, and also the Indonesian spices. And then they can sail all the way in here. Yes, I remember the name of this city. This is Beirut. So if I now tell you that in the past, Beirut was a port city, you'll be scratching your head, right? Okay? So there is a port city in China that is somewhere down here. Okay, it's in the middle of the continent, but it's a port city nonetheless, because ships can sail right up to it. They don't sail in the sea; they can sail up rivers. So port cities, we have to be a little bit creative and imaginative. Port cities are anything that a ship can reach. Okay, and Beirut is in fact one of the important ones, and I think there are other important cities in the Middle East that are not that near large bodies of water, but can be accessible through rivers. And of course, the Venetian ship will sail. So I don't know why the animation comes here. The Venetian vessel is supposed to come from here to Beirut, and then go back. Okay, and what we intend to explore would be, how agents like these kind of sailing vessels react to changes in the environment, like seasons, winds, currents, and commodities like silk, ceramic, and spices, and to political changes like wars, treaties, and dynastic changes. And of course, what we want to see whether we can use this agent-based model together with the data. Of course, I'll mention the data later. What is the maximum possible value of global trade? Because we don't believe that whatever is recorded is actually the close to the maximum, because there's always a lot of slack in this kind of systems. And what is the specific turnover at specific port cities? And then we can do scenario analysis. What if Ming China stopped trading earlier? Ming China actually stopped trading somewhere in the middle of the period that we looked at. Because of internal political strife. That the two groups of eunuchs cannot agree with each other. So one group doesn't want the other group to have control over the port cities and start earning money through trade, so that's why they stop trading. Of course, that doesn't stop the Chinese from coming to Southeast Asia, because they can always legally set off in the middle of the night when the court officials are not watching. And what if the Portuguese started exploring earlier? So these are all what if questions. And the reason why we choose this was because we then have to work with a very short period of time, which is about 300 years, from 1200 to 1533. But it's already global in scale and complexity, because this is the dawn of globalization. So this is a map of the trade networks that are already in existence since many years ago. Around the region, but they first become connected in the 1200s. They first become connected. In the past, this trade would operate more or less independently from this trade. So if you look at the time series, they'll be uncorrelated. But they first become correlated around 1200s, at least according to the historians, and we would like to test that. Okay? And then there are primary sources available. So I am in collaboration with a historian, which first of all, he is the one who curated this set of Venetian diaries. We also have the Ming Chronicles from China, and then we have also official documents in the Venetian archives that we can look into. They are all scanned, but they're not translated, and there's no optical character recognition because of the very variable handwriting in those days. And we want to set ourselves the goal of doing this strictly bottom up. It's never been attempted before for an agent-based model. So let me introduce the team. So this is the historian that I work with, Andrea Nanetti. This is another historian at Princeton. He's the one who supplies some of the data on the trade that is going on. We're also in collaboration with Rosario Mantegna. So he will be solving one of the problems for us, and then I am responsible for developing the agent-based model with the help of Coy, who is a final year physics undergraduate at the Hanoi University of Science, but he's right now in my lab because he's doing an internship for his final year project in my lab. And in order to collect the data, we need to build something like an agent-based data template. So this is meant for the historians, not so much for the modeler. In this data template, the historians need to fill in things like this: agent types and agent names. As far as the productivity is concerned, the historians need to read through the records and then see what the preferred actions are and under what conditions these would happen. And then for reactivity, the same. What are the original actions? What was the environmental feature encountered? And what was the new course of action? And for interactivity, they have to keep track of all this stuff, fill it into an Excel file, and then send it to us. And then we realize that we are in for a rough time, because the historians are never going to stop updating this file. So when are we going to do the simulation? Until they finish updating the file? No, right? So they are going to update the file. One historian will finish it, and they say, please simulate and let me see what is the outcome. So I would like to do that. Okay, and then after 3 weeks later, another historian say, I've just finished updating my part. I want to see my simulation. So I'm not going to do one agent-based, I'm not going to write one agent-based simulation for the first historian, and then later on write another one from scratch for the second historian. To think of this more cleverly, and then the software design would be like, we plan of it, doing it this way. So first, we have the historians filling in the agent-based model data template. This alone is not enough for simulation. We need to have agent definitions. So we need to be able to convert from the agent that is type that is recorded in the template into actual software code. So we also need to do it for actions. So these two files, programmers must develop it. And then we will feed all this into an agent-based model compiler, because we realize that the compiler, this solves the problem of us having to completely rewrite an agent-based model simulation every few weeks or every few months, because the compilers need to be updated only very infrequently. The ABM data template can be updated as frequently as they like it to be. And then after that, we will produce something like an ABM executable. It's just another file that we will plan to assemble in Python. But in this way, we solved the first problem of the historians working on the agent-based data template, and us being able to not have to rewrite an agent-based simulation all the time. Then we run the second problem. The agent-based data template is extracted from primary sources. So primary sources, you realize that the people in the past, they don't write down everything. All those things that everyone knows, they don't never write down. For example, I'm sure here in Chennai, nobody will write down that you drive on the left or on the right. You just say you drive. So then when we have to run the simulation, we need to choose one side. But it is again it's not in the record. So there are lots of gaps in the primary sources. So in cases like this, we need to be able to have a separate set of inputs. It's called inferences, to be able to fill up the gaps in the primary sources. And in fact, secondary sources exist. So these are written by historians that they effectively have gone through the entire process, short of building the agent-based model to fill out all the gaps, and they've written books about it. So these can be built into libraries that can be read in by the ABM compiler in order to create any number of ABM executables. So this is the software design part. And our preliminary experiment will be to test these various aspects. So we have tested all this stuff here, but I'm just going to show you self-avoiding random walk. How much time do I have? Okay, 10 minutes. Oh, okay, that's a lot of time. So I'll slow down for a bit. Okay, so I'll show you the MATLAB code for random walk written by physicists. I mean, basically, I think only physicists would be interested in writing simulations for random walk, which is very simple. So this is something written in MATLAB. So these are all the moves that are possible. There are 5 of them. This is to move north, move east, move south, move west, and then stay put. Okay, just 5 moves to get all together, and you initialize the random walker at 0, 0. Okay, then you run for t time steps. T can be anything you like. T can be 100, can be 10,000, can be a billion time steps, up to you. And then you make a choice here. You make a random choice here. I equals to a randomly, uniformly distributed integer between 1 and 5. So basically, you decide which of these moves you want to make at this point in time, and then you make the move, and then you repeat. So this I should be a little I, and then you end. So you can see that the MATLAB code for a random walk is very simple. But the problem is, who made this choice? Okay, so when you talk to a physicist, a computational physicist, he won't care. Why does it matter who made the choice? You just run the simulation. And from the point of view of a historian or a humanities scholar, this choice is made by God. It's not made by the agent. Basically, God decides that, oh, I'll choose this move now here. You do it. Okay. And that's obviously, that's not a manifestation of human agency. So top-down agent-based simulation frequently is written from God's point of view, not from the agent's point of view. So I'll show you what we can do with the agent-based simulation software design, but also, to think about the agent-based simulation purely from the agent point of view. So the agent must be able to be the one to make all the choices, react to the environment, and this is something like this. So this is a supposedly complex domain on which the agent will do the random walk. So we start the agent off in the corner of the F-shaped domain. So the red colors are cells that are marked, but they are the walls. So the agent is never supposed to be in there. Okay, and these are all the preferred actions. These are the conditions. So you see that here the conditions are none. So the agent is free to go anywhere if it is allowed. But of course, if it lands at the wall, then it needs to go back to the previous location. So let's see what happens. Okay, so initially, the agent made a choice to move to the east. So when we say that the agent choose to move to the east, basically in the program you will see agent.choose move. So the agent is the one that makes the choice. So although there is some rolling of the dice, it is the agent that rolls the dice. So, and of course, every agent will roll its own dice. There will be no supernatural being involved in that decision. And we also mark this previous position of the agent red because we are trying to do something called self-avoiding random walk. So the random walker must never revisit a location that it has been to before. So this is marked. Now this should be separate because this is actually God's point of view. Because everything that is not the agent belongs to God. So the environmental features are managed by an entity that exists outside of the agents. Otherwise, the agents make all the decisions. So that's one move. And then after that, to the south. And after that, to the east. Then stay put. Then to the south. And then to the west again. And then to the north. And of course, anyone would be able to see from God's eyes view that this agent is now in trouble because he's completely trapped. So there's no place that he can go. But let's say the agent doesn't know because the agent needs information and it doesn't have the information until it interacts with something. So let's say the agent walks west. Oh dear, it walks into the wall. Okay, so this rule here is now triggered and he goes back. So the reason why this agency of the agent, the random walker, is manifest is because the agent actually tries to make a move. The environment says no. So there's information that is transmitted to the agent, and then the agent chooses a new course of action. So this is why we think of this as a manifest agency for the simulation. And of course, this agent can then go to the north. But this is a cell that's already visited. In fact, it started from here. So it's now, because under the rules of self-avoiding random walk, this is not allowed. So it gets kicked back to the original site, and that's it. That's the end of the simulation. Okay, so we tested this thing, it works, and right now we're testing for interactions between agents, and again we need the agency to be visible. We need to be able to see that there is human agency involved, and I think I've come to the end of the talks. I hope you have interesting questions you can ask. So as to the purpose and outline of and aim of this workshop, can economics become a physical science? So nowadays all the sciences are trying to become data science. So we must well take that extra step and ask, can economics become a data science? And the answer is yes, if we if we look into the example of the data going from Brahe, the data, to Kepler, the model, to Newton, the mechanistic modeling and in theory. So there are scientific approaches that we can adopt for observational science, and there's also scientific approach that we can adopt for big data science, which will actually incorporate machine learning and data mining in the very first step to generate the hypothesis. And can we do bottom-up agent-based simulations? We can. And the reason why we don't do top-down agent-based simulation is because the historians will continuously update the agent-based data template, and then they will become experts in typing the simulation very quickly, but we don't want to be like that. So for our proof of principle project, we chose to work with the historical network of port cities because the data is available. We developed the agent-based model data template for the historians to work with, and then we will provide the agent definitions as well as the action definitions, and then the software framework for enabling this agent-based simulation is what the computer scientists have already invented and used, and that is source compiler executable framework. And then we would introduce inferences as well as secondary sources as libraries for the simulation. And preliminary experiments we have done. We have done a lot of preliminary experiments already, but the one I've just shown would be the self-avoiding random walk on a complex F-shaped domain. So the reason why the domain is complex is because it doesn't only have walls. It also has the cells that are marked because the agent has been there before. Now this is of course a highly simplistic demonstration, but you can imagine more complicated interactions between the agent and the environment. For example, we can have two kinds of agents, red and blue agents. So red agents will mark the cell red, and blue agents will mark the cell blue. And then after that, a red agent may never visit a blue cell, and a blue agent may never visit a red cell. So that will be a different kind of random walk. So it will be a competing kind of random walk. And of course, later on when we finish testing the interaction between agents, we can have agents doing simply basically denying each other the right to be at a cell, or we can have agents passing each other pieces of items or information that they can use to do something else. For example, we can have a bunch of agents in doing random walk, and the aim of this random walk will be to find a leader.